Okay, so welcome to this third lecture on the topic of hardware security. So today we will be trying to understand how to map algorithms to hardware. So this is essentially this talk will be covering few aspects on hardware design. So we will start with understanding about what is meant by data path and control path. We will be trying to understand or identify data path and control path elements to implement algorithms. We will be trying to see like data path and control path design in the context of an example. So this example is based on a GCD processor or a greatest common divisor computation processor. And finally, we will be trying to see how we can do design exploration, because designing is one thing and exploration of the design is another aspect. So how do you design is one aspect, but how do you also explore various opportunities and various implications of your design? How do you analyze the scalability of your design? So we will be considering FPGAs, as I mentioned that k input LUTs. So in this case I will be taking k equal to 4 and we will try to model the design, and we will try to understand how the performance scales in our design. So to start with, when we map an algorithm to hardware, I mean you understand that performance is the main reason why we do hardware design. So definitely like that is a primary goal of a design. So for an efficient design, like if you really want to understand how to efficiently implement an algorithm in the form of an architecture or an hardware, so you need to understand the components of the hardware. Okay, so you need to understand what are the basic blocks which a hardware is made of. Okay. So there are two important aspects in a hardware. One is the data path, the other one is a control path. Okay. So data path are basically those things which constitutes the computational units of your design, and the control path essentially sequences the data path element. So it basically kind of switches, it kind of loops around in that along the data path elements. So it basically does sequencing of your data path computational blocks. Okay. So in this diagram, for example, you can see that there are three important blocks. For example, there is a data path, there is a memory, and there is a control path. So the idea is that when you take inputs, for example, the inputs are processed by both data path as well as the control path, but data path essentially comprises of the main computational units. Okay. So they essentially does your processings. Okay. Some of these data may also be residing in the memory. So it may happen the data path element needs to fetch some data from the memory and also write back into the memory. And the control path essentially kind of communicates with both. So basically it kind of talks with both the data path as well as the memory and tries to communicate and tries to sequence your operations. Okay. So let us take an example. So this is an example of a binary GCD processor, a very common example straight from the textbooks. So you see that there are two integers u and v, and what we are interested is to compute the greatest common divisor of u and v. So in this case the greatest common divisor is stored in the variable v. Okay. So just to parse through the binary, so this is also called the binary Euclidean algorithm. So you can see that the algorithm is a sort of a modification of the original long division Euclidean algorithm for computing the greatest common divisor. So the algorithm is broken up into certain parts or certain possible branches. Okay. So the first thing is that you check that whether u and v are same or not, because if you know that u and v are same, then you have a trivial result. If u and v are not same, then you do or compute this in a recursive fashion. Okay. So what you first check is that whether both u and v are even. If both u and v are even, then you can say that okay, if the greatest common divisor of u and v is z, then that is same as if I take 2 or factored out 2 and compute the GCD of u by 2 and v by 2. Okay. So that comprises your first branch here. Okay. So this is this branch which I am talking about. Else it may happen that one of them is even, say u is even. In that case I can divide u by 2 and compute the greatest common divisor of u by 2 with v. Okay. Or it may happen that u is odd and v is even. In that case I will just divide v by 2. Okay. So I know that since one of them is odd and the other one is even, 2 is not a common factor. Okay. Or it may happen that both u and v are odd. In that case I will just check whether u is greater than equal to v. So I will, if u is greater than equal to v, then I will subtract out v from u, and I know that if there are two odd numbers and if I subtract, right, then I get an even number. So I can divide this by 2 because I know that v is not even, so therefore 2 does not divide v. Okay. So therefore, I can write this as greatest common divisor of u minus v by 2 with v, and if it is other way around, instead of doing u minus v, I do v minus u. Okay. So now what we want is, we want to realize a coprocessor on FPGA to compute the greatest common divisor of two given numbers, but I want to use this algorithm. I want to essentially kind of map this algorithm into an hardware block. Okay. So in order to do that, first we will try to identify the states of the algorithm. So that is the first step. Okay. So this is a sequential design. We can understand that is a sequential design. It kind of does the computations in not like a combinational design like in one shot, but it does in over several iterations. Okay. So the first thing that we try to do is, we try to write the code in a format which is like an HDL language, which is something like a Verilog language, for example, or a VHDL language, but it's not exactly an HDL depiction of the algorithm. Okay. So what we try to do is, we try to kind of think of a possible, we try to first of all think about how do we store u and v. Okay. So the first thing is that we think of a register transfer logic, okay, on an RTL description. So here we know that there are two variables u and v. So in order to store u and v, I allocate two registers, say XR and YR, which I use to store the values of u and v in my computation. So here the first thing is the assignment, where I essentially assign u to XR and I assign v to YR. Okay. And then I initialize a count to 0, why I will come explain very soon, but this is the first step. Okay. Now what I do is, in the algorithm, what I see is that I check whether XR is not equal to YR. So this is straight away from the previous algorithm, because it was u not equal to v in the previous algorithm. Here I have to check that the first thing which I have to check is that whether both u and v are even. Okay. And the way I can check that very easily, if you think of a hardware or like an implementation of the algorithm, is what you just need to check is that LSB. You just need to check the least significant bit. If the LSB is 0, then you know that u is divisible by 2. Okay. Likewise for v. So what I just check is the last bit of XR and YR, and if it turns out that both of them are 0, then I know that we have an even number. Okay. We have both u and v as even. Okay. So then what I do is, if you go back to my algorithm, what we have to do is, we have to divide this by 2, right? We have to divide u by 2 and v by 2. Okay. So how will you do this in hardware? The usual way of doing this in hardware is doing a right shift. So here we do a right shift of XR and we do a right shift of YR. Both are equivalent to saying that I divide them by 2. And then if you remember that in my previous algorithm, right, I have to factor out 2, but rather than doing that now, I just keep a count of the number of times I am doing this operation. Okay. So what I do instead is, I kind of increment a counter, and count was initially 0, and I start incrementing count like count plus plus, okay, or count equal to count plus 1. So this is one part or one state of the algorithm. The other step which I will, or other possibility which can happen, is that again one of them is even and the other one is odd. Okay. So it can happen that either XR is even or YR is odd, or it can happen that XR is odd and YR is even. So therefore I kind of again do a similar thing here. I just check the LSB of both XR and YR. If XR 0 is 1 and YR 0 is 0, I do a step, which is like I know that if this happens, then Y is even, and if Y is even, I will just right shift Y. Okay. I will not disturb XR. Okay. Likewise, if it happens in the other way, right, then I will disturb XR and not affect YR. Okay. The other possibility is that both of them are odd. That's the else part here. So here again I do a comparison between XR and YR. If XR is more, then I just right shift XR minus YR. Okay. So basically I do u minus v by 2. Okay. That's an analogy here. Likewise, right, I do YR minus XR, and then when finally all of this is done, that means when I exit this while loop, I come to this point, and remember I have a value of count to indicate like how many times I have taken out 2. So how I can do that is, what I have to do is I have to multiply 2 count times, right? So I have to do 2 to the power of count into XR, or 2 to the power of count XR. So 2 to the power of count means I have to kind of left shift XR each time. Okay. So therefore I left shift XR count times, and that is equivalent to saying that I am doing 2 to the power of count. Okay. So, I do 2 count, then 4 count and so on, okay, in powers of 2. So, if you see this algorithm, therefore, we can say that this algorithm has got 6 states. I have numbered them from 0 to 5. So, this is my state 0 where I initialize, this is my state 1 where I check that both of them, this is one possibility, right. All of these states are basically indicating some unique configuration of your algorithm. Okay. So, here you see that state 0 stands typically for the initialization part, whereas state 1 stands for the case when both of them are even. State 2 and state 3 stands for the cases when one of them is even and the other one is odd, and state 4 stands for the case when both of them are odd. Okay. And state 5 stands for the case when I'm almost going to give you the output. Okay. So, that is the final output state. Okay. And here after very soon we will get the result, which is being stored in the register XR. Okay. So, this essentially is a very like a very simple example, but we will see like that you can actually apply this technique to implement even complex algorithms. Okay. So, it is important that we understand how the state assignments are done and how we translate subsequently to a hardware design. Okay. So, now let us see that how do we identify the data path elements. So, basically as I said, data path elements are nothing but computational units. Okay. So, let us try to see what are the computational units which you have already used in your design. Okay. So, if you see for example, the elements or the components which you have used are typically shifters. You have used right shifters, you have used left shifters, you have used adders. Okay. So, basically you have done subtraction which can be realized by addition. So, definitely we need a subtractor here, and we also need comparisons. Okay. And comparators you can also implement with by a subtractor. Okay. So, therefore, you virtually, right, if you count the number of or the data path components, then you have a subtractor, you have a complementer, you have a right shifter, left shifter and counter, because you also have counted. Okay. The other element which is not very explicit here is a multiplexer, because you see that there are several branches in my algorithm. So, these branches are essentially inferred as multiplexers in hardware, because multiplexers essentially gives you a select logic. Okay. So, either you go in this path or you go in other path depending upon the value of the control logic. Okay. So, multiplexers are required in large numbers for the switching, which is necessary for computations done in the data path, and the selection lines in the multiplexers are configured by the control circuitry. So, therefore, each multiplexer will have a select line, and this select line, right, will get values. So, these values will be given by the controller, will be given by the control path. So, therefore, what we have to do is that we have to sequence the data path elements, we have to place the data path elements, we have to place the multiplexers. The multiplexers will be receiving inputs. Okay. So, the data path inputs will come from the data path elements, but the control input will come from the controller. The controller will basically configure the multiplexer and will kind of switch so that your data path sequence gets configured. Okay. So, therefore, right, that is what we had to discuss about the data path component. We also have the control path. Okay. So, the control path, as I said, is a sequential design. Okay. So, therefore, the data path is largely a combinational design, but the control path is a sequential design. So, in this case you can see that it is a 6 state machine, because we had 6 states in my algorithm, and the controller in this case receives inputs from the partial computations of the data path elements, and based upon the current state and the input it performs state transitions. It goes from like in between all these 6 states and produces control signals. Now, these control signals are what configures the data path elements or the switches. Okay. So, they basically gets configured, the data flow gets sequenced, and that essentially is done explicitly by the controller. The controller generates these control signals which configures the multiplexers. Okay. So, I believe that this will be more clear with this diagram. So, here you see that this is the overall architecture. So, we have got a data path element. So, this is your correspondingly your data path component, and here is your controller logic or control path. Okay. So, basically, right, this splitting of an algorithm into 2 components, the data path and the control path separately, is a very important or central part of VLSI design, at least when digital design is concerned. Okay. So, in this case you will see that we can try to understand how this hardware works. So, the first thing which you note is that the data path stores the values of XR and YR in two registers. That means, when you get the value of u and v, you load them in XR and YR. Okay. So, therefore, XR and YR are two registers, and they are actually loadable registers, which means there is an explicit load signal which is indicated as by this signal called load underscore XR. When load underscore XR is high, then XR gets loaded. Likewise, when load underscore YR is high, then YR gets loaded. Okay. So, the values of u and v are initially, so you see that there is a big mux which I have placed here, which I call as the mux A. Okay. So, it is actually not one single mux, but it is kind of comprised of several muxes. Okay. So, it is kind of a symbolic logic. So, what it stands for here is that it receives some inputs. So, it receives, for example, load underscore uv. So, load underscore uv, when it is 1, then initialization happens. That means, u and v are being loaded into XR and YR, and of course, you have to also make load underscore XR high and also load underscore YR high to load the values of u and v into the registers XR and YR. Okay. So, therefore, once these values of u and v are initially loaded, then we start our processing. Okay. So, again, like the state machine sees the values of XR and YR. So, these XR and YR, or rather the XR 0 and YR 0, which means the LSB of XR and the LSB of YR are being transferred to the controller. The controller sees these inputs, because that is very important for our control path design. So, it probably tries to understand whether both of them are even, both of them are odd, one of them is even, the other one is odd. Okay. So, based upon this, these list bits of XR and YR are now passed to the controller to indicate whether present values of XR and YR are even or not, and then the next iteration begins. Okay. The next iteration values of XR and YR are essentially like based upon certain computations. Okay. As we have seen in the algorithm, you have to do some computation. So, for example, you have to do a subtraction, you have to do a shifter, and so on. Okay. So, therefore, depending upon the after whatever is the needed computation, you do them, and then you have to update your XR and YR. Okay. So, you have to either update both XR YR, or maybe you have to update one of them. Okay. So, this logic is essentially told by this signal, which is called as update underscore XR. So, update underscore XR or update underscore YR basically tells whether you have to update XR or you have to update YR, or you have to update both, or any one of them. Okay. So, therefore, so what are the computations which we are doing on XR and YR are subsequently enlisted. So, the first thing which we have seen is the division by 2. Okay. And as I said, the division by 2 is done by 2 right shifters. So, therefore, you will see that in the data path there are 2 right shifters which are placed here. So, this is one right shifter and this is the other right shifter. Okay. So, these are the 2 right shifters which have been placed. Okay. The other thing which you have to do is you have to do subtraction. So, you have to do an equality check, trying to understand whether XR and YR become same. Remember the while loop condition. Okay. And the other thing which you have to do is to understand whether XR is greater than or equal to YR, or XR is lesser than YR. Okay. So, this you can do, both of them you can do by a subtractor, because the first one is an explicit subtraction, the second one you can do by a complementer, which is in the 2's complement. So, therefore, that also you can realize by a subtractor. So, what we do here is, therefore, we place a subtractor here followed by a complementer. The subtraction is a usual subtraction between XR and YR, and depending upon whether the result is like negative or positive, you do a subsequent inversion of the result. So, therefore, if you do not want XR minus YR, you complement it to get YR minus XR. Okay. So, therefore, the circuit also has got an up down counter, as I said, because so therefore, finally once before that, right, before I go into that. So, after you have done these operations, right, and you want to kind of load your data into XR and YR, you see that there are 2 ways in which you can probably load. Okay. So, if you go back to the algorithm, you will see that the 2 possible ways or where you can load is you either update XR directly, that means you just right shift and update XR, or it may happen that you do a subtraction and then update XR. Okay. So, this logic, okay, is encapsulated by this signal. So, this signal is told as or written as load XR after sub or load YR after sub. That means, if load XR after sub is high, then rather than taking the result from this point, which is just the right shift actually, what you do is you take the result after subtraction. Okay. So, you basically take the result after subtraction and then right shift. Otherwise, you take the result directly from XR and right shift, okay, and then you update XR. So, these are the 2 possible things which can happen. Similarly, for YR. Okay. So, once this process is done, you have to basically, there is an up counter, which essentially, as I said, you did an incrementation of a counter, and finally, right, when you are at the final state, that is at S5 or state 5, you also can do a left, you have to also do a left shifting. Okay, so there is a shifter which can either there is a counter which can either count up or it can count down. Okay, because when you are when you have done so remember that when we are doing this when we were in this part of the loop, that means when we were in this part of the loop, we were counting up. Okay, and when we are in this part of the algorithm, then we are counting down. Okay, so we are either counting up or we are either counting down. So this means that the counter that we have should be an configurable counter. It should be an up down counter. The counter can count up as well as can count down. Okay. So that is essentially the elaboration of the data path of the algorithm. Now we can come to the state machine of the algorithm. So in the state machine, as I said, that there are 6 states starting from S0 to S5, and what we try to see over here is how the control how the state transitions take place. Okay. So I have just tried to explain few of them. For example, I mean, I believe that we can understand the remaining from from these examples. So in this case, the controller receives 4 inputs from the data path. Okay. So if you see right here, the controller receives some inputs. So these inputs are XR not equal to YR, XR is greater than equal to YR. So likewise, right, there are 4 inputs which the controller receives. So it receives XR is not equal to YR, XR 0, YR 0, which are the LSBs of XR and YR, and the result of the subtraction, that means XR is greater than equal to YR or not. So all of them can be indicated by 0, 1 values, right. So therefore, these essentially determine the state transitions as well as also has got influence on the output of the controller. Okay. So for example, if your present state is S0, that means you are at the initialization state, then your load underscore UV is 1, load underscore XR and load underscore YR are both 1, because you are loading both XR and YR with the content of U and V. Okay. And suppose you receive an input which is denoted as 0 and followed by 3 don't cares, because the moment you see this being 0, you know that this is 0. That means XR is not equal to YR is 0, which means XR is equal to YR. Okay. And what you do in the algorithm, if you remember, right, if you see XR, if you go back right to the algorithm and check what you do when you see that, so this loop, right, this while loop continues when XR is not equal to YR. So that means when XR becomes equal to YR, you exit the while loop and you come to state 5. Okay. So therefore, exactly this is what is being depicted here in the state machine. That means whenever you see that this happens, you know that the next state is S5. Okay, and that is essentially tabulated in the table. Likewise, if you receive an input which is 1 0 0 cross, which means like XR is not equal to YR, and you see that both XR 0 and YR 0 are 0, that means both of them are even, then you see that the next state is S1, because remember that the state S1 was which was processing that particular scenario, right. I mean XR, this is the state, right, that is when both of them are even, then this is the state which is handling this. Okay. So therefore, you need to jump to state 1. Okay. So therefore, that is exactly what is done here. The next state is S1. So likewise, when you see the present state is S1, okay, so if the state is S1, then at this point you see that what you essentially do, right, if you go back to the algorithm, is when you see that both of them are even, then I mean, for example, right, if you go back to the algorithm and check what is exactly done here, you do a right shift of XR and a right shift of YR, and you update XR and YR. Okay, and you also upcount a counter. So now if you go back to the state table, then you see that what you do exactly is this: you make load underscore XR and load underscore YR both 1. You update underscore XR and update underscore YR also as 1. Okay, and an update counter is also 1. That means you also have to increment your counter, and whether you are incrementing or decrementing is denoted by this signal. Okay. So likewise, again you receive inputs like 0 cross cross or the 0 don't care, don't care, don't care. So in this case, again you have to make the next state as S5. If you get 1 0 0 cross, then you have to make the next state as S1. But if you get an input like 1 1 0, then you know that XR is odd, and therefore your next state has to be S2. Okay. So that is what you have essentially done throughout the state transition table, and you essentially can populate the entire table in this fashion. Okay. Now, once you have done that, right, you basically have your hardware. So, your hardware, right, you should implement this in Verilog, and you should have the data path and the control path, and essentially it should be like as I said in the previous class, you have to simulate that and see that it indeed does a GCD computation. Okay. So, now we essentially come to the next part, or the exploratory part, where you have to do a performance evaluation of the design, because as I say that one of the primary goals of developing a hardware design is performance. Okay. So, but performance is context sensitive, like depending upon like several your application, you may either want like to make it low power, or you want to make it fast, or maybe the objectives are different. But broadly, right, in a combinational circuit, the most important aspect what you want to optimize is the critical path delay. Okay. So, the critical path delay, right, essentially is often predicted by the synthesis tool, which tells you, right, that from register to register what is the maximum path. Okay, and that kind of gives a bound on the maximum frequency that you can operate. Okay. So, for example, your maximum frequency, right, at which the clock frequency FCLK can operate is say f max. Okay. So, likewise, right, for the sequential, so if you take or consider sequential circuits, then along with the critical path, the other important thing is the number of clock cycles which you need to compute. Now, if you observe the GCD processor that we just now discussed, right, it is not a constant time implementation. Okay, that means, right, depending upon the inputs u and v, the number of clock cycles which will be required can vary. For example, in this case, it will be proportional to the bit length of the bigger argument. Okay. So, therefore, on an average, right, if you denote the number of clock cycles as CC average, then the total computation time will be CC average by f max. Okay. So, if the number of bytes of data being simultaneously processed is NB, then another very important parameter is what is called as throughput. Okay. In this case, the throughput will be denoted as NB by TC, because TC is the time which is required to do a computation, and therefore, you will get something like NB into f max by CC average. Okay. So, this can denote the throughput of your hardware. So, when you are making a new design, these are the parameters which you have to quote about your design and show how competitive it is. Okay. So, now when you want to make a design, right, the other important thing is the resource consumed, because you also want to make your design more compact. Okay. So, therefore, let us take a look back at our structure of the LUT. So, this is the structure of the LUT for Xilinx Virtex 4, where the LUT has got 4 inputs. So, it is basically realizing any 4-bit Boolean function. Okay. So, now if you take these two functions, like these are both Boolean functions y1 and y2, one of them is an XOR of x1, x2, x3 and x4, the other one is an XOR of x1 and x2. Okay. So, you see that in terms of gate equivalence, one actually takes only one XOR, whereas the other one takes 3 XORs. Okay. So, I would expect that this one will be more consuming than this one. But if you consider FPGA designs, which is slightly different, you see both of them will take one LUT. Okay. So, I will say therefore, the first design which actually does more computation is actually still needing one LUT. That means it is utilizing the LUTs better. Okay. So, therefore, Y2 results in actually an underutilized LUT. The LUT is not maximally utilized, because you see that once you have realized Y2 in that, you cannot realize any more function in that. That is, the remaining part is kind of a waste. Okay. So, therefore, what we want, right, is we want to make the number of unutilized or underutilized LUTs as minimal as possible. Okay. So, how do we do that? So, here we, without like going into the derivations, you see that we can model them pretty accurately. Okay. So, what we can do is, for example, the number of LUTs for a q-bit combinational circuit, that means a combinational circuit which has got q inputs, for a 4-input LUT can be modeled by these equations. Okay. So, you see that I have kind of covered different cases where q is 1, then of course, I do not need any LUT. Okay. If q is less than 1 and 4, then I need one LUT, but if it is more, then depending upon 2 cases, I can pretty much say that is like the seal or the floor of q by 3. Okay. So, the other important parameter is the delay. So, again like delay is a very hard thing to compute in FPGAs, but if you just want to compute the number of LUTs which lies in the max path, then you can pretty much accurately model that by log q base 4. Okay. For a k input LUT, it will be log q base k. Okay. So, and then I multiply it with the delay of the LUT to get an understanding about what is the delay for say log q base 4 LUTs. Okay. So, therefore, this gives me the delay for a q-bit combinational circuit. Okay. So, now if the question is, right, if I want to know what is the percentage of underutilized LUTs, then you observe that there can be, so I denote LUT k to denote the fact that the k inputs out of 4 are used. Okay. For example, in my previous case, y1 was LUT 4 because I had got 4 inputs to the function. Okay. y2 was a 2 input, so it was LUT 2. So you can say in that case, right, that LUT, if I consider LUT 2, LUT 3 and LUT 4, then LUT 4 is not wasting any lookup table, but the remaining things, that means LUT 2 and LUT 3 are what are contributing to your underutilization of lookup tables. Okay. So therefore, the way in which you can calculate the percentage of underutilized LUTs is by adding LUT 2 with LUT 3 and dividing by LUT 2 plus LUT 3 plus LUT 4. So you will get an sort of an estimate about the underutilization of the lookup tables. Okay. As I said that for FPGAs, because in FPGAs you don't only have LUTs, but you also have routing delays, it is really complex to analyze delay. Okay. But from experiments you can see that if you take combinational circuits, then the delay will actually vary linearly with the number of lookup tables in the critical path. Okay. So here is an experiment that we did for some combinational multipliers, and for this combinatorial design, if we start increasing the dimension of the multiplier and we start plotting the delay with the number of lookup tables in the critical path, then we see a more or less linear relationship. Okay. So therefore, we can pretty much accurately predict the delay, or at least understand the trend of the delay by using the number of lookup tables, or by like giving an estimate of the number of lookup tables which lie in the critical path of my design. Okay. So once we have these two formalisms, right, we essentially can start modeling the components of the greatest common divisor. Okay. So if you see in the greatest common divisor, the other very important component is the adder. Okay. Now modeling the adder by these lookup tables is slightly tricky, because here we can observe that in most of the FPGA circuits there are dedicated adders, okay, which means that we have got the normal lookup tables, but there is also an additional chain. Okay. Now this addition chain is much faster compared to the normal LUT delays. Okay. So in order to understand that, what we did is we basically incorporated a scaling factor. You can incorporate a scaling factor which will essentially say that like if you want to kind of estimate the delay of your adder, then for an m bit adder the delay can be estimated by m by s, okay, and seal of that. So that means right, you are basically reducing or trying to incorporate the speed of your carry chain. Okay. So for vertex 4 you can estimate that s will be around 17. Okay. That means, right, if you are so now with this value of s, you can actually like compare the adder delay with other lookup table components. Okay. So it kind of brings it to the same platform. So therefore once you have these tools, you can observe that you can model the multiplexer. Remember that a multiplexer is a 2 to the power of t is to 1 multiplexer, which means that there are t select lines and there are 2 to the power of t inputs. So therefore the multiplexer is a Boolean function of dimension 2 to the power of t plus t variables. Okay. That means the number of variables to the number of input variables of the multiplexer can be modeled as, or can be enumerated as 2 to the power of t plus t. So therefore if you fit into the previous expressions, then the number of lookup tables will be around, you can model it by LUT 2 to the power of t plus t. So 2 to the power of t plus t is an argument to the LUT function that we just now mentioned. So therefore for an m bit GCD multiplier, the number of lookup tables is m into LUT 2 to the power of t plus t. So here m is an m bit. So therefore you can visualize that each multiplexer is each multiplexer can be broken up into m multiplexers. So all these multiplexers are working in parallel. Okay. So therefore the number of lookup tables will be m times the number of lookup tables which are required to implement one multiplexer. Okay. And the number of lookup tables to implement one multiplexer is LUT 2 to the power of t plus t, and that I multiply with m to get the overall number of lookup tables. Likewise, right, you can get the delay mux. The delay mux is 2 to the power of t plus t, and you do a log with base 4, okay, and therefore you get an estimation of the delay. You exactly fit into the previous expression and you get an estimate of the delay. So now if you want to kind of estimate the LUT of the overall design, so you can see that you have got mux A, mux B, mux C and mux D in the, so there are 4 multiplexers in your architecture, and there are 2 subtractors. Okay. So therefore the overall, the total LUT count will be 2 times that required for a subtractor plus the summation of all the 4 multiplexers. Okay. Similarly, you can, so in this case actually I have ignored the lookup tables which are required to the state machine, for the state machine, assuming that that is much lesser compared to the data path components. Okay. Likewise, you can also calculate or estimate the total delay. So in this case, this is your data path. So again you can see that there are 4 multiplexers, mux A, mux B, mux C and mux D, which we essentially already accounted for while counting the number of lookup tables. If you see the delay, right, this is your critical path. So we start from this register and we come back to this register. Okay, so that means it starts with the subtractor, goes to the complementer, goes to this mux D, comes back to mux B, and finally goes to mux A. Okay, so you can estimate the delay in this way. You can estimate the delay in this fashion. Okay, so for example, it says like 2 m by s plus 1 plus 1 plus 1. So in this case, it is 3 plus 2 m by s, and therefore that gives you the overall delay. Okay. So why you essentially bring in one delay for the mux is because you can visualize, although it's a big mux or it looks like a big mux, you can visualize this mux to be made up of 2 multiplexers, one multiplexer for updating XR and the other multiplexer for updating YR, and both of them have got delay of 1 lookup tables. Okay, so or 1 lookup table. So therefore we write here 1 for each of these multiplexers. So with these estimates, right, you can actually try to experimentally validate. So the idea is that you can try to take a Vertex 4 device and take a Xilinx ISE tool or any other FPGA tool and can try to repeat this experiment for different versions of GCD. So you can do GCD implementations for different bit lengths and try to see how your design scales. Okay, so you will get some estimates from the CAD tool, and you can use these modeling estimates also and try to see how well they correlate. The reason why these models are useful is because if you have these models, then without doing the design, you can actually gauge the sort of the performance of your design, and therefore you can make decisions early in the design cycle. Note that it is very important to do or take decisions early in the design cycle because it can save a lot of time and manpower. Okay. So therefore, right, I mean, here is an example of how your lookup table scales. So you see that we have got a very much like a close following, although like the LUT estimations that we had were actually minimal. That means this is the minimal number of LUTs you need to implement. Okay, so therefore, right, it matches pretty well. If you see the delay, this is the delay estimation, although it doesn't match exactly, but you still see that the trend is predictable. Okay. So I have given two plots here. One of them is for when you have flattened the hierarchy, and the other one when you have not flattened the hierarchy. So these are, so the flattening means like if you take a design, right, you have got different modules in your design, but when you flatten them to one level. That means you have got one single level, and the other is like when you have kept the hierarchy on in your synthesizer. That means that you essentially are maintaining the hierarchy of your design. Okay, so you will get slightly different estimates for them. So, this is a reference that I have used for the discussion, and so what we basically discussed is that it is very important that we do a proper division of data path and control path, and that's a key for hardware design or hardware architecture design for an algorithm. Always we have to start with a nice architecture diagram, that is the 0th step of VLSI design, and performance modeling can be useful tool to guide the exploration. More than accurate estimation, one can observe trends in the design which can be helpful in making early decisions in your design cycle. Okay. So with this, thanks for your patience, and hope we will again continue on the subsequent topics in the next class.